Good morning and welcome you all to this session of the course on fluid machines. In the earlier few sessions, we were discussing about the radial flow reaction turbines, which is named as Francis turbine after the name of the American engineer who contributed a lot to its development. So, in Francis turbine, we have seen that it is a radially inward flow turbine. Flow at the inlet is in mostly the radial direction. It has got radial and tangential component of velocity, and the bulk flow is in the radial direction, radial inward, and while it is coming out, it is purely radial and the tangential component is kept almost to 0 to have the minimum kinetic energy at the outlet. Now, one thing has to be remembered, please have a look on this turbine, that this is the typical runner blade or runner of the turbine, and you see when it flows through this has a radial and tangential component of velocity at inlet. When it comes outward, then it has purely radial velocity, which is turned 90 degree in the axial direction while enters into the draft tube. Now, one important thing that we already discussed also is that this reaction turbine is efficient at low head. That means, if it has to run efficiently at a lower head or a higher specific speed, then what happens to develop a considerable power, it has to admit a large amount of flow into the turbine. That means, the flow rate has to be high if the head available is less and it has to work efficiently. But at the same time, it is already appreciated that the velocity of discharge at the end has to be low. That means, the velocity at inlet to the draft tube has to be low to avoid cavitation. So, that the pressure at inlet to the draft tube does not fall below the vapor pressure of the working fluid, that is water at the working temperature. So, to maintain this criteria, that two criteria, that velocity low at the discharge and accommodating high flow rate, what is required is the cross sectional area of flow should be large, which is difficult to maintain in a purely radial flow turbine. Moreover, the cross sectional area in the direction of flow has to decrease the static pressure of the working fluid, because you know, the reaction turbine, the static pressure, there is a drop in the static pressure and drop in the static head for the fluid as it flows through the runner blades or the rotor blades. So, therefore, in this type of converging passage in purely radial flow at the outlet, it is difficult to accommodate high flow rate with maintaining low velocity. This has evolved the concept of axial flow turbine. That means, if we consider the turbine blades or the runner blades such that while the flow enters in the radial direction, it has got mostly the radial and the tangential component of velocity, but while flowing through the runner, this radial velocity is gradually changed to an axial direction. That means, flow direction is gradually changed to an axial direction, and finally, at the outlet, if the entire flow comes axially, that means, entire velocity of flow or the absolute velocity becomes axial direction, then we can accommodate more area. That means, if the blades are twisted like that to make the outlet axial, outlet cross sectional area normal to the axial direction, it can provide more area and to accommodate more flow. And this gives rise to the concept of axial flow turbine. Actually, this is known as mixed flow turbine, where the inlet is radial and inlet velocity components have both radial one and the tangential one, while flowing through the runner blade the direction of flow changes gradually from radial to axial, and while it comes out of the runner exit, substantial part of the velocity component is, that means, the substantial part of the velocity component is in axial direction or purely axial. This type of runner is known as mixed runner. while it is entirely axial flow, that means inlet is also axial, the fluid is directed by the guide blades in such a way that the flow already becomes in the axial direction, and through the entire runner blade it flows along the axial direction and comes. That means if it is a horizontal turbine, the flow changes like this and it flows along the axial direction, that is in the vertical direction, which is the axial direction of the axis of the rotating shaft. So, this type of flow is turbine is known as axial flow turbines, and this can accommodate very high value of cross sectional area of flow, that is the area of flow in the horizontal plane perpendicular to the axial direction, and can accommodate a large quantity of liquid flow rate, mass flow rate of liquid, and can work more efficiently at a very small head or high specific speed. So, this is the basic concept, originating concept of the axial flow turbines. So, now here we see that how the development of axial flow turbine has been evolved here. If you see that, of course, it is difficult for you to see here. Now, let us see from here. Now, here you see this is a purely Francis turbine, a radial flow turbine. Here the blades are like this, which is at the inlet, the diagram which we already recognized, that this is the inlet flow velocity or inlet absolute velocity. This is the component normal to the tangential direction, and that is known as the flow velocity Vf1. I think you can see this very well. This is Vf1 and that is V1, and this direction is radial. This is normal to the tangential direction. That means liquid at the inlet, water at the inlet for example, has a absolute velocity which has substantial component in the tangential direction and also in the radial direction. In a purely radial flow machine which works at a relatively higher head as compared to an axial flow machines, amongst the reaction turbines, a purely radial flow machine works at a relatively higher head when the specific speed is less. In that case, the flow velocity, that is Vf1, velocity normal to the direction of flow, is less, is relatively small. So, large part is in the tangential component. However, this is basically a radial and tangential flow at the inlet, and the inlet velocity is very high. This is Francis runner for a low specific speed, means at this for low specific speed, that means the head is relatively higher. Now, when the specific speed increases for normal specific speeds, from low to normal means there is an increase in specific speed or reduction in the head available. So, therefore, as I have told, when the head available is reduced, that demands relatively more flow through the runner. So, runner blade is designed in such a way that at the inlet the flow velocity, that means the radial component of velocity which is responsible for the mass flow rate at the inlet section, is increased, while the absolute velocity of flow at the inlet of the fluid at the inlet is reduced. The guide vane angles are same, but the blade is designed in such a way, and the guide blade area, the guide vane area is adjusted in such a way that at inlet the absolute velocity is reduced as compared to that for low specific speed case, that means relatively higher head, and at the same time this Vf1, this is also Vf1 is more than the earlier one. That means, as the specific speed increases, we see there is an increase in the flow velocity and a reduction in the absolute velocity of the water at inlet. Similarly, you see this is Francis runner for high specific speed, that means from normal specific speed to high specific speed. So, from normal specific speed to high specific speed, that is when the head is still lower, that is there is an increase in specific speed, the turbine blade or the runner blade is made such a way, this angle beta 1 here you see in the tangential direction, if we define this angle, this was obtuse. Now, here this has become 90 degree. That means, this is the velocity of flow and which is coinciding with the relative velocity. That means, not only it increases the velocity of flow, at the same time the blade at the outlet is in the radial direction. That means, radial at the outlet. So, that the relative velocity and the flow velocity is coinciding with each other. That means, this value beta 1 is reduced to 90 degree. This is 90 degree. This is another aspect. Now, when we still increase the specific speed or reduce the head, it should admit more fluid, and in that case this is curved in this way, so that we get an acute angle for this beta 1, and this becomes the velocity triangle, where the absolute velocity of water at inlet is still reduced and this velocity Vf1 flow velocity is further increased. That means, what we see up to this is that as we go on increasing the specific speed or reducing the fluid head at the inlet, then the flow velocity is gradually increasing and the absolute velocity of water at inlet is gradually decreased. This is done to accommodate more mass flow, but up to this the flow is almost in the radial direction. So, it is a purely radial flow turbine. It follows almost the same geometry of Francis turbine, but when the specific speed is much larger, that means the head is really reduced, then what is done? We arrive at a turbine known as Dove's runner. I write it D-U-B-B-S, Dove's runner. This is known as Dove's runner. What is done? This is a mixed flow turbine. Here the entry is radial and tangential. Here you see the entry is, here the flow velocity, that is the radial component of velocity, that is perpendicular to the tangential direction, is much higher compared to all earlier three situations, and at the same time the absolute velocity at the inlet is reduced. But the difference is that inlet flow geometry is same, that means it is mostly the radial and the tangential, but the tangential component is less, but the radial component of the flow velocity is high. But while flowing through the runner blades, it changes its direction, it becomes more in the axial direction, and when it comes out of the runner here, the blades are made such twisted, so that direction changes, and at the outlet it becomes axial. That means, if you think in this way, I cannot show you a figure, you probably can download a figure from net. I do not know whether you can get it or not, that this is the turbine runner. In a Dove's runner, it comes like that and the blade itself is twisted like that. When it goes out, it is purely in the axial direction. If the runner is in the horizontal plane with the vertical shaft, it goes in the axial direction, and this is a typical Dove's runner. And when the flow rate, the specific speed is still higher, that means it is huge high value of specific speed where the head is substantially low, we go for a purely axial flow turbine, which is known as Kaplan turbine, after the name of the Austrian engineer Victor Kaplan. So, this is a purely axial flow turbine. Here the inlet and outlet both are axial. Inlet and outlet both are axial. The blades are made in such a way that inlet and outlet, the blade looks like the propeller of a ship, and less number of blades are there. That means the flow, that if you think in this fashion, that if this be the turbine, the flow is like this. That means it is in the axial direction. That means the guide vane at the inlet already turns the flow to the axial direction. So, turning takes place to the guide vane, and the entire flow through the runner is in the axial direction, both at inlet and outlet. And this type of machines have less number of blades and provide a very high value of the cross sectional area in the horizontal plane, which sometimes we tell as frontal area, that is normal area to the direction of flow, and can accommodate a huge amount of flow rate and can work at a substantially low head or a very high specific speed. And this turbine was developed much by this Austrian engineer Victor Kaplan and is named as Kaplan turbine. So, here you see in a Kaplan turbine, this is Vf1, that flow velocity, which is very high, but the difference between this with the other one, the flow velocity here, which is perpendicular to the tangential direction at the inlet, is radial flow. That means flow in the radial direction, because at the inlet it is tangential radial, but at the outlet it is radial, but it may be axial in case of Dove's runner. But in case of Kaplan runner, this is Dove's runner, Kaplan runner, the inlet is also axial. So, therefore, this component which we call as flow velocity, that is the velocity in the direction of flow, which is perpendicular to the tangential direction, it is axial. That means, this is axial component. So, this is axial component, that is the difference. And here all other cases, these components are the radial components. So, flow velocity, which is the velocity in the direction of flow and perpendicular to the tangential velocity direction, at the inlet is in the axial direction. But at the outlet velocity for all runners are like this. Outlet velocities are all runners are like this. What is the similarity for all runners outlet? That the absolute velocity at the outlet does not have any tangential component, does not have any tangential component, the outlet velocity, to keep the kinetic energy outlet a minimum. Okay. But the difference is that in all runners except Dove's and Kaplan, where the outlet is in radial direction, there this velocity, the absolute velocity, equals to the flow velocity at the runner, which is nothing but radial velocity, radial component. Whereas, in case of Dove's runner, the outlet is axial, and in case of Kaplan runner, that is purely axial flow machine or axial flow turbine, inlet and outlet both are in axial direction. So, therefore, this velocity, absolute velocity, which is equal to the flow velocity, in this case for Kaplan and Dove's runner, this Vf2 is the axial component, axial component. Okay. So, therefore, we see how the concept of axial flow compressor evolves from that of a purely radial flow runner with the increase of specific speed or with the decrease of head available at the turbine inlet. Okay. Now, we will see in actual a picture or figure of a Kaplan turbine, which is sometimes known as propeller turbine. Here you see that this is the shaft, this has got a vertical, this is a vertical shaft, this is in horizontal plane. This is the runner, which looks like the propeller of a ship, and this is the runner blade. Okay. We see a frontal view, this is the runner blades. The number of blades, number of runner blades are usually 4 to 6 limited, and it provides a huge normal area of flow. Now, these are the guide blades, and this looks like this propeller, this entire runner looks like the propeller of a ship, is rotates in this direction in a horizontal plane, the shaft is vertical. Now, these are the guide vanes, this is guide vane, this is already written here, guide vanes. So, flow comes like this, inlet. So, guide vane turns the flow right angle to this. This is turned by the guide vane and then flow through the runner blades and purely in the axial direction. This is the axial direction. This is the axial direction. So, therefore, what happens? The guide vane turns the flow 90 degree and makes it to flow in the axial direction. Now, you see, while the guide vane turns the flow, there is a curvature like this, is a geometry of this casing, and the flow gets some tangential velocity. Some tangential velocity is imparted in the flow, some amount of swirl is imparted in the flow as it reaches the turbine blade, and this swirl in the static part or the stator of the machine can be considered as that of a free vortex flow if we discard the effect of viscosity, where the tangential velocity is increasing with a decrease in the radial location from the axis of rotation. That is the free vortex, the rule, that is the relationship of the tangential velocity, which is inversely proportional to the radial distance from the axis of rotation. It can be approximated more closely with a free vortex rotation, but the rotational motion of the blade is solid body rotation, which is a forced vortex type. That means solid body rotation, where the angular linear velocity is proportional to the radius of rotation, that means radial location from the axis of rotation. A combination of these makes a complex flow of a typical Rankine vortex type, which is a mixed of solid body rotation and the free vortex flow. So, away from the center there will be free vortex flow, close to the center of rotation is the forced vortex flow, and to take care of that these blades are made twisted. So, in axial flow turbine, the runner blades are twisted blades, where the angle of the blade, that is the angle means the angle of the tangent to the profile of the blade with the axial direction is more at the tip and less at the root. This is regarding the geometry of the blade, and this is a view. If you see from the top, this is the view. There is 1, 2, 3, 4, as I have told, 4 to 6 runner blades. These have 4 blades. Okay. Now, after this, here just recall one thing: the head, that is energy or head energy per unit weight, is 1 by 2 g, that is imparted to the rotor by the fluid, V1 square minus V2 square, okay, plus U1 square minus U2 square, plus V. If you recall this, at the some beginning sessions we discussed, where V1, V2 are the absolute velocity of water or fluid at inlet and outlet, U1, U2 are the runner bed velocity at inlet and outlet, and VR2, VR1 are the relative velocity of the fluid with respect to the runner at the outlet and inlet. Now, in case of an purely axial flow machines, U1, U2 component is 0, there is no change, because the inlet and outlet are always at the same radial location. So, you can define the runner velocity at any central plane, that is mean radius of the runner. Now, therefore, this is the change in the dynamic head. So, this is the static head. So, the change in static head will be obtained only by the change in the relative velocity. That means, if you want that the reaction machine, it is a reaction machine, obviously there will be a drop in the static head, that means the static pressure. So, we have to change this relative velocity, that means this has to be positive in that case. So, VR2 has to be more than VR1, which means the flow passage, that is the flow area, cross sectional area normal to the direction of flow, that is normal to the axial direction, should be a converging type. So, therefore, an axial flow machines may be purely impulse machine or may be a reaction machine. For purely impulse machine, what we have to do? We have to make the flow passage, that means the flow cross sectional area uniform, so that there is no change in the relative velocity. Okay. So, therefore, it will be an axial impulse machines. There are machines which are axial flow but impulse, but axial reaction, for axial reaction machines, the axial flow turbines are axial flow reaction machines, where the flow passage is a converging type, that means the cross sectional area perpendicular to the direction of the flow. In this case, it is the axial direction. There is a reduction in the area to increase the relative velocity to get a drop in the static pressure or static head of the fluid, okay, in the runner. So, this has to be also kept in mind. So, this is axial flow turbine, and this is suited for very high head and low, very high specific speed and low head available at the inlet to the turbine. Okay. Thank you.